page 3 of your parametric, polar, and vector packet, you have a discussion of arc length as it pertains to parametric equations. So we're used to just having a function in terms of x or a function in terms of y. And so when we explored this concept of arc length in the previous chapter, it was always in terms of y or in terms of x. So throwing in the third parameter requires that we just adjust our formula for arc length just a bit. So at the top, you have two formulas that you guys should already know of for arc length. And just to refresh your memory on where those formulas came from, if we're given a curve, so the idea of arc length is to find the measure of how long a curve is that might not necessarily be straight. So let's say you have a curve, and we will just find, for example, the length of this curve by dividing it into, like we do with everything else, into really small segments. So let's assume that our segment, just so that it's visually appealing, we'll make it larger first and then talk about the idea of reducing the size of the segment. So for now, our really small segment is this segment here. And so if we were to come up with what the length of the blue curve is by using small segments, dividing it into small segments like the one you see here that's in pink, we can find the length of a straight segment by using distance formula, or what we call Pythagorean theorem, where the distance formula comes from. So if we refer to the bottom leg as change of x and the vertical leg to be change of y, then we know, according to distance formula, that the length of the pink segment should be equal to change of x squared plus change of y squared. And that is the arc length formula that we're used to seeing. Now, when we proved the formulas that you see highlighted, what we did was we divided each one of these terms by either change of x squared or change of y squared. And then we integrated to sum up the infinite number of little segments that you have. So for this purpose of parametric equations, we're going to have a third equation, this time in terms of t. So rather than dividing change of x and change of y respectively by change of x squared or change of y squared, we're going to do change of t squared. Now notice some adjustments I'm going to make is I'm going to make this radical sign just a little bit bigger, put in change of t squared inside the square root on the bottom as a denominator. So effectively, I've divided by change of t squared inside a square root. But if we think about what the square root of change of t squared is, then we get a value of change of t. So ultimately, what we did was we divided the entire expression by change of t. To counteract that, we would multiply by change of t on the outside. So take a moment, what we just did was multiply by change of t over change of t, where the change of t was just incorporated inside the square root. So when we bring it inside the square root of change of t squared is the same thing as just change of t. So overall, we have change of t times over change of t. That's what we multiplied by. So now in looking at this, if we divide the larger segment into smaller segments like the pink segment, but make it even smaller, what we're doing is we're bringing the points together, reducing the distance between the 2 points, and eventually going to infinity. So we approximate that using an integral, the integral for summation, summing up an infinite number of those segments. So the formula, the third formula that we're going to have for arc length is the integral from t equals a to t equals b, the square root of, and I'm going to change the delta symbols to be dx dt and dy dt, also differentials for representing change in x and change in y, and then rewriting it as dy dt quantity squared, dx dt quantity squared with a dt on the outside. So summing up an infinite number of really small segments. Now, the questions that pertain to arc length we saw from first semester were really hard to ask in the non-calc section. There are a few that end up being in the non-calc section, but for the majority of the questions, they will be calculator questions. So go ahead and write for example number 4 that this is going to be a calculator question. So they want us to find the length of the curve of x equals and y equals those expressions. And this is a calculator-based question. So what we're going to do is find dy dt and dx dt separately. So dy dt is 1, and then positive e to the negative t is the derivative. Chain rule on that is going to make it negative because we're timesing by -1. Dx dt is equal to e to the t minus 2t. And then what we're going to do is plug it into the equation where our interval is from -1 to 2. The square root of, don't forget to square your expressions, but e to the t minus 2t dx dt squared plus 1 minus e to the negative t squared dt. If I can have you guys take out your graphing calculators, you're not going to be expected to understand how to do parametric equations on the calculator in terms of having to change the mode. So if I'm looking at this equation, it's like replacing the x variable with t. In this case, everything's in terms of t. So when you're trying to come up with the integral with this variable here, you're just going to use the x t theta symbol that you guys have been using for your independent variable. You don't have to make sure that that's equal to t. So that's one source of confusion for students. So go ahead and enter in the integral of this and evaluate it on your calculator, and make sure that you guys are matching that it should be equal to 4.497, always round to 3 decimal places. And if not, if you didn't get that answer on the calculator, I want you to make sure you try it on the calculator. If you don't get that answer, screenshot what you have and send it to me on Remind, and I can help you guys out from there. Now, example number 5 is an example that is on the non-calc section. So let's say non-calc. And so that's going to require a bit of algebra for us to be able to find the antiderivative. So let's go ahead and find respectively dy dt and dx dt. So go ahead and do that. So as you guys find dx dt, you're taking 3/2 times 1/3, so you're left with 1/2 out on the front. You've got to reduce the exponent by 1, so subtracting 2 over 2, you get 1/2. And then times by the derivative of what's inside, which is just 2. And then from there, you'll simplify the 2's out, and you have just 2t plus 3 to the 1/2. So what you'll notice with the non-calculator section is that it does simplify out to be really nice expressions for you to be actually able to integrate. So we're going to integrate from 0 to 3. The square root of 1 plus t squared. Doesn't matter if we interchange x and y, or dx dt and dy dt squared. So we're squaring that derivative, each one of the derivative expressions. And we see that we're left with a binomial that we have to square out, FOIL out. And then this one, if you square the square root, this will undo each other and you're left with just 2t plus 3. So in order for us to integrate, we're going to have to make sure that we're able to somehow reduce it down to something that is easy to integrate. So what I'm going to do is start to FOIL out. Remember that you've got 1 plus t times the quantity 1 plus t, which is not 1 plus t squared. Right, because we've got the middle terms that we have to FOIL out as well, which is 2t plus t squared. And then this expression, again, is just 2t plus 3. Usually what this is going to result in is something that is factorable again. So we have t squared plus 4t plus 4. And as you guys examine that, you'll notice that you can factor that to be 2 plus t quantity squared. And that way, when you take the square root of something square, you end up with just t plus 2. And notice that I have not done any integrating. So at this point, we would find the antiderivative, get t squared over 2 plus 2t, and plug in our 0 and 3. We get 9/2 plus 6. If I plug in my 0 to subtract out, I get 0, 0. So my final answer, 21/2.